All right, those who are online, can you hear me? Okay, can you hear me? All right, I think you can hear me. So welcome back to CAB 6640. And before we get started, so there's a little bit of introduction and a recap of what we have been discussing last time. So starting with the lecture objectives. So we want to highlight some logistics, then go over WordNet and its limitations, then opening directions for encoding as an alternative to WordNet for computational representation. Then we will start with one more serious representation that kind of alleviate some of the problems that we will discover in encoding, and it's going to be word-to-vec and distributional representation. Then we will go over gradient descent and stochastic gradient descent, as well as a little bit of an example that can highlight more technically how we deal with word-to-vec in real life. So before we get started, so there are logistics. Module 1 was released, and so I had a little bit of an issue going to the office from here. So we started the recording here in Zoom, and then when I went to the office, I realized that the recording was messed up. So I had the dimensions of the video messed up. So some of it was truncated, and so I had to a little bit of tricks to be able to recover that. But at the same time, in the process, I realized that, like, okay, so if I want to put my voice over with the technology that we are teaching in this classroom over my slides, taking in the like the actual contents of the lecture, polishing them a little bit, and then putting them in recording. What is the best tool for that? I don't want to do that again myself. I don't want to just like sit in front of the computer and just like speak the same thing over and over. And so I it's not really fine tuning. I just like masked my voice over a large language model, a voice language model. It's called XTTS v2. And I was able to produce 2 versions of all the slides. One version with my voice on with all the you know, whatnot, and then interruptions and students asking questions that nobody else is basically hearing it online. And then another version where it is like more smooth, like AI delivered. And so I put those on YouTube, share them during the time that you are supposed to see them, and you can choose which one you want to go over, whether it is the long one with the imperfections or the perfected, revised after the class type of one delivered by AI. And believe it or not, this is the best I could kind of come up with as a voice that is similar to my voice with the tuning. So I sound like a British person in that AI generated thing, but this is what we have. The recommended book is released, although it does not cover everything that we will talk about. And the proposal is due on January 20th, which is today. The similarity issue is to be avoided. And so one of you have emailed me asking about what happens if I get the similarity, all due to the copyrighted block at the bottom of the form. And I posted in the announcements 2 ways to resolve the problem. Either use the minimal document I provided you, or if you know how to use LaTeX, then just plug those 4 lines of code at line 65 in the original code that I gave you. So try to remove, or not try to remove, you must remove the copyright block, which creates the similarity or inflate the similarity. Come again? There are enough instructions there, so just follow the instructions. Okay, I don't know like what you need to put there. I'll grade based on the rubric, which I already gave you. Okay, academic activity is going to be due 23rd, on the 23rd, and so even though the academic activity is not a required component in this class, it is only required for those who need that for improving academic involvement, and that is oftentimes for financial aid. I would invite everyone to do that. It's very simple, very easy. Whatever point you get is a bonus point, so do it. And then assignment number 1 is going to be due on January 26th. Do not push that to the last minute, so start working on the assignments as soon as possible. With that, let's just like recap what we kind of stopped at last time. And so we were talking about how to get representations or deliver meanings or useful meanings to computers. And one of the most common solutions to the problem, early solutions to the problem, was what we call WordNet. which is using lists of words depending on the relationship and their types and whatnot. So what we call synonyms sets and hypernyms or relationships between those words. And this is a great, it works when it does, but it has some problems. This is great as a resource that can be used to understand relationships between words and enumerate synonyms, but it misses some nuances that are common in the language. And so those include the exact, precise usage of the word. So for example, proficient might be listed under the same word good as a synonym, which proficient does not necessarily mean good always. This is only correct in some very specific and narrow contexts. Also, the other issue is that it can miss new meanings of words, and those meanings are a result of the nature of languages as a dynamic way of communication. So, for instance, some of the words that can be just used in certain contexts, like wizard, genius, ninja, bombast, and so forth, to highlight capabilities, are in you. They are not necessarily standard, and nevertheless, they are words for communication. So you want to communicate this meaning to the computers, and WordNet does not capture these meanings. It's impossible to really keep up to date without a significant amount of effort that you have to encode those new meanings into the WordNet. There is also varying levels of subjectivity, in the sense that we as humans use different words to mean different things, even though the meaning does not fall under the standard meaning. It requires human labors to create and adapt. I mentioned that earlier, and cannot compute accurate word similarity. For instance, you cannot tell if, say, good is related to bad. It's a positive, but it's related to bad, especially if it is in a general context. Or good is related to goodness, for instance. So that is that. So this is an issue. This is a problem. And so you can imagine that we want to address those problems using some techniques. And so we start presenting those techniques by looking at the simplest, then just like evolve a little bit to get to where we want to get with the neural network-based kind of representation. So the simplest of that is to represent words as symbols rather than as just like words understood by humans. And so in traditional natural language processing, we regard words as discrete symbols. Like, for example, we can refer to words as hotel, conference, motel, and those are going to be localist representations. So these are like words. The example that we have, for example, cat or dog or fish, these are symbols, like just abstract symbols. And they are good when they work. So we have seen them in WordNet, and they are kind of cool, understandable, easy, but do not really answer a lot of the problems that we have of symbol representation. So one way to represent them even at a lower abstraction is through what we know as one-hot encoding or one-hot vector. So imagine that you have, like, say, for example, 10 words in a dictionary, and that's all you have. You can represent each of those words with a symbol. Choose it of your own choice, like, make it of your own choice. Could be like, the first word is going to be A, B, C, D, E, F, G, right? This is good. This is great. But imagine that you have a large number of those, okay? Large means like, 500,000, for instance. So one way to do that is to just use this very simple idea of one-hot encoding, meaning that for the index of that particular word, the first word, you just like have one, and then the rest of the representations, the rest of the indices is going to be zeros. So, and so forth. So like in the second word, you have the second index in that representation to be one, and the rest is zeros. And so imagine that we have our dictionary to be cat, dog, fish, and this is all we have. Then you can create a one-hot encoding of size 3, right? And so the first bit is going to be 1, and the first bit for the index for cat is going to be 1, and then 0, 0. And then for dog is going to be the middle 1, and then 0, 0 for the others, and so forth. So here, the vector dimension is what? Is 3, because our dictionary has only 3 words. But imagine that you have like 500,000 or a billion words. I mean, there's no language that has billion words, but let's imagine that. Then you want to have 1 billion bits for representation. Very sparse representation. Only the information for a given word is only represented in a single bit, and then the rest of it is going to be zeros. So this is good, but it has some problems. And I guess everyone can here foresee those problems before we even talk about them. So example, so I'll highlight those problems with the example. So the example that we have here is web search. So let's say, for example, if users want to search for Seattle motel, let's say motel. They are looking for a place to stay. They are visiting Seattle and they want to search for Seattle motel. And so also we want, in the process of retrieving this information from back end, to also provide the users with other results that are similar. So for instance, hotel, lodging, hostel, whatever that is, okay? So house or Airbnb or whatnot. So Seattle hotel, so we want, basically things that match Seattle hotel and motel and hostel and whatnot. And let's say that, like, Seattle is the common word, so we want to focus on the word hotel, motel, hostel, or Airbnb and whatnot, okay? And so the problem happens, the first problem happens when you get the representation of motel and the representation of hotel, and those are not similar in any way in the representation. Hotel would be like, one bit somewhere there. If we talk about like alphabetical order of the words, it's going to be very far somewhere. And then motel under M is going to be some other where. So like one and one, but you cannot compare them computationally. You cannot like say that they are similar to one another computationally. And in a sense, this is two problems, not only one problem. The first problem is that those vector representations that we have are mathematically orthogonal to one another. What does orthogonal mean? Let's highlight this idea with this very simple example. Let's say we have the Cartesian. We have two dimensions only, x and y. This is the representation that we have had earlier, like these 1, 0, 0, 0, 1, 0, and 0, 0, 1. So orthogonal means that the angle between them is a right angle. Okay, this is the representation. So you can imagine that in this Cartesian, a 0, 1 is going to be 1 on the y-axis, and a 1, 0 is going to be 1 on the x-axis. So they are orthogonal. You cannot calculate similarity between them. The distance always going to be the same between all words. Okay, there's going to be a right angle between all words. And I'm here giving you the example in 2D because it's easy to explain. But you can imagine that even in a higher dimension, that this distance is going to be the same between all the kind of words. So this is bad. So orthogonal, and you cannot calculate distance between them. There is no natural notion of similarity for the one-hot encoding, one-hot vectors. Make sense? Okay, this is one. Yeah. Oh, we'll talk about that in a second. Yeah.
So maybe a dumb question.
No, there's no dumb question.
We're talking here, or the context of this discussion, natural language processing is spoken word, right? Not necessarily written.
Either one. So you have eventually the spoken word itself can be written as a written word. Like you can have a phase where you just like get anything spoken and put in writing. And this is what we want to get. Let's talk about only written contents for now. Text.
Fine with that.
Okay. Yeah, but the same idea applies to even spoken languages, because like the spoken utterances, you can envision that as a voice, and you can have the voice as token. Each word can be tokenized to be like a signal. Yeah, right. Some like filtering, you'll be able a word, and the word is like what we are putting here. So the word, the motel is going to be one somewhere, and then the hotel is one somewhere, and you want to say that motel and hotel without, like, you as a human, you are supervising this process and you know the answer, but a computer does not know. And so if I'm giving a word to the computer, I want the computer to retrieve the words that are similar to that word, like, for hotel, motel, house, whatnot, right? Things of similar nature. And here's what we are struggling with. So there is no way to calculate similarity. And this is a good question. And a good question in the sense that later on we will realize that it is a difficult problem to treat sound like image, like whatnot, like text, and that is like what we call the multimodal type of structures. So okay, this is a problem. The problem is that those are orthogonal, and you cannot calculate a distance between them. You cannot calculate similarity. Distance means that you just find out which one is similar to another one based on this distance. We can think of some solutions to the problem. So the first solution is we could try to, basically rely on WordNet, which we explained earlier, and calculate the similarity between words. Not exact, not precise. It has all of the caveats that we can think of, but it's still better than nothing. Okay, it's better than nothing. But this is like a patch. it's not really like a solution to the problem. It still like will fail badly. It has incomplete examples. You have scale it, whatnot. So we are just like getting back to the same problem that we tried to avoid in the first place. The second solution to the problem is that you try to learn to encode similarity in the vector itself. So instead of having one, you can have some distributional representation that is going to add some values in different parts and different bits so that it captures similarity. So you can calculate some distance between them and make things that are similar to one another different from, similar to one another, close in this representation, and the ones that are different from one another, far away in representation. So instead of having like one in one place, you have some values, and this is going to be your code for this word. Another word that is similar, you're going to have a bunch of other values different from other words. It's unique in a sense, but close in distance to the similar words. That's what we want to achieve, okay? So again, what is the problem with this? Okay, what is the problem with this? The problem with this is that it is just something that does not capture the similarity, okay? And it has other issues, but this is really out of scope for what we're trying to achieve. So this is what brings us to distributional semantics. So what you want to do is that you want to do the representation in a way that you capture similarity. And so the idea of representing words by context, that words that are similar are going to be represented in a similar way, and words that are different are going to be represented in the same space, but different in a different space, in different parts of the space, is that we rely on the context of the word. The context of the word will define it. Okay, so words' meanings is given by the words frequently appearing close by it. So for example, if I want to define the word hotel, what are the things that can define hotel, right? So you say like, I stayed in a hotel, the Hilton Hotel, and so forth. So there are like a few words in the language that happen to appear next to this word in just general natural utterances, and those in a way define the word. Okay. Any questions? All right. So there is this very famous statement by J.R. Firth, who said that you shall know a word by the company it keeps, you shall know a man by the company he keeps, and so forth. This is like a common statement, and we want to emphasize this idea. And this is basically one of the most successful kind of ideas in natural language processing today, is that you want to have this distributional representation. It's not like the one-hot encoding, and you want to rely on the appearance of the word in context. Yes, please.
It could be a semantic problem and not a pragmatic.
Representation?
Then
yeah, you're fine. It's representation. I don't think that we want to basically map everything that we learned to those three things that we learned, okay? So, and I made that clearer maybe in my further notice, is that semantic tasks are something that is shallow. It's like you don't want to understand the deep meanings of anything. You just like want to have a shallow understanding of a task, surface level kind of understanding. Anything that tries to understand intent and meanings and whatnot is going to be pragmatic. But pragmatic, in a sense, is something that takes context beyond individual word, right? It's a more meaningful, useful task in real life. A single word does not really, it's a construct for something bigger. And that's why I'm afraid of saying that, like, oh, consider it this way or that way. Just like, there are certain things that are underlying those definitions, those are groups of definitions. So I don't want to go there. So for this context-based representation, away from the one-hot encoding, when a word W appears in text, the context itself will define this word. We'll use that to define this word. So we use many contexts over and over, and then maybe aggregate those contexts to find out a good vector representation of the word based on the many contexts it appears in. And that can be generalized really to any dictionary. So for instance, you say the government debt problems turning into banking crisis, as happened in 2009. In other contexts, you have saying that Europe needs unified banking regulation to replace the whatnot, and India has just given its banking system whatnot. So you can define the word banking by the bunch of words that are around it. So for example, banking in the first case, turning into banking crisis, you can define banking with turning into crisis, need unified regulation, and given its system, if we are assuming certain window size of definition for the word's neighborhood. Okay, make sense? Now, you might be asking, oh, how are we gonna represent the word into, or turning, or crisis, or need, or unified, or regulation, or given its system to be able to get this word banking as a representation? Any thought? Like a trivial way. I'm not gonna, basically ask you for explaining to me word to Vic, because we'll explain in a second in a probabilistic way. But what is the trivial way to do it? How? So we have already like one-hot encoding. Let's stack those vectors of one-hot encoding for the word into or unified or whatnot. Stack them, right? And then add them all together. You get a vector representation. Normalize it. So, like for example, it's was like the number one, let's say it was the first word has one, right, and so forth. You add them together. Like you can add vectors, right? So you align the vectors in this case, like the case that we have here. You align those vectors and say like the word horse can be defined by cat, dog, fish. Then we will add them together. It's going to be, of course, we have four vector of size 4. And it's very unlikely that horse is going to be defined by cat, dog, fish, but for only clarifying that with an example. You can stack them together. Stack them means like, add them together, the vectors. You'll have like 1, 1, 1, 0. Let's put horse at the end. 1, 1, 1, 0. And horse is going to be defined by this vector representation. That's a trivial idea. Bad idea, but this is like more of, in a sense, this is what you could proceed by doing, right? And imagine that language is going to be very rich, sizable. So you're not going to have like only 4 words. So you talk about like, a word appearing in context based on a large corpora, right? On a large data set, then you will be able to get differentials between words. Like you're not going to get like, 1, 1, 1, 0, right? Moreover, you can represent that as you can flatten it, normalize it, and make it as a distribution. Make it a probability distribution, right? Bad idea still. It's a very bad idea because the meanings need to be learned.
Something where you can kind of tell it, or the system starts figuring out based on dialect or based on previous. I think that's what the other person over here was saying. Like there has to be some previous context you're operating in, because
we are going to that. That's why I avoided answering this question, right? Yeah. So I'm asking about the simple way to do it. Like how will you think about in a simple, trivial way about it? What kind of representation that you want to get? You want to get a representation of a word based on its context, based on the peoples around it, right? And so those words around it from a large number of occurrences, it appears like, the word banking appears like 1,000 times in a given passage, in a given like book, for example. And you want to represent it in that book based on how it appears in that book. So you extract all the words around it, and you say like those words define this word. And then get a representation for the word banking based on the representation of all those words. And it's going to give you a continuous distribution. Okay, make sense? Okay. So now this does not work. Why? What are we doing here? The word like the initial representation that we had, one-hot encoding, is a very sparse kind of representation. Imagine that you have 500,000 words. And stacking those words together to define a given word is not going to solve the problem. It's going to solve one problem only, the similarity problem, right? You can calculate similarity because words that are similar to one another are going to appear in a similar context. And so you can calculate the distance between them. I know it's like the distance is small, cosine similarity is going to be small between them. And then I can then solve this problem. But then the other problem is going to be dimensionality. You'll have a high dimensional space that you're representing those words in. So it's going to be very inefficient. Make sense? Extremely inefficient. This is one. Another thing is that like I'm not really sure about like how good this representation will be for distance, right? We do not know. So we have to have something smarter. So word vectors is what we have here. We do not want to do that kind of silly idea. We want eventually to do something that is more elegant, something that is compact, I want to have compact representation. I want to have only like 100 values in a vector instead of 500,000 stacked. And those are going to be in the continuous spectrum. Value can be like, of any precision. Can be like a point something, 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 up to like 32, full precision, or 16, or whatnot. Very fine, like kind of floating values. So I can adjust them to separate words, make words closer to one another based on some tuning or whatnot. And this is what I want to have. And this is what we call the word vector. It's a compact representation of a word that will, in a way, make words that are similar to one another, close in representation, and words that are not similar, dissimilar to one another, far apart, okay, based on distance. Quick question here, a refresher. How do you calculate the distance between vectors? Victor, we forgot about character now. We are talking about words like banking and financial represented as those vectors. Let's say that this vector has a size of 1, like the width of it is 1, and then the height of it is going to be 50 values. And you have 2 of them. One is for banking and one for financial. And financial and banking are words that are similar to one another. So how do you calculate distance between them, between those vectors? Yes. Dot product, the cosine similarity. So those are simple things. For those who do not have that, just you get the absolute difference between the values, you sum them, and then get the average of them. Okay, the absolute difference between them. So the distance, the difference between them, like 2.25. I'll highlight that with an example in the next slide. But you can imagine like 0.255 and 0.215. You get the difference between them, and you have like a vector of differences. You sum that vector of differences and then average it. That could be like one potential distance. So the average absolute difference between the pairwise distance, of those representations. Okay, and this could be a single value, like 5. The distance between them is 5. It can't be 5, but 5. Let's say it has to be less than 1. Cosine similarity. So 5. So if I know that the distance between banking and financial is 5, and distance between banking and dog is 100, then I know that banking and financial is similar or more similar to one another than, say, for example, banking and dog. Make sense? Okay. Dot product. Yeah. So it's a dot product or cosine similarity or any other similarity you can use. Okay.
Lower value.
The lower value, the more similar they are to one another. Okay. 0 means like the same word. If you have like 2 different words that have 0, like they are 0, like the distance between them 0, then you have a terrible system of representation, very bad system. Okay. All right. So like what we want to eventually do, we want to have representation. Here we are trying to simplify things. We are projecting things on the Cartesian so that we can together understand what's going on. And so let's say that we have words of similar nature. Say, for example, has, had, have. We want to have those words to be close to one another in representation. We have, say, for instance, think and meet. They are like action verbs. Think, say, expect. Come, go. Take, get, give. Become, be, remain. We want to have them close to one another because they are similar in a way. And you can make separation between verbs, for example. It does not have to be a verb to be, yes.
Yeah.
Like what? Yeah. Oh, that is like, we will talk about that in a second. Like, remind me at the end if we not cover it. Okay. And so eventually what I want to have, by the way, this is exaggeration. If you know a little bit about mathematics, you know that this is like nonsense that we have here. It's like high dimension, and then we are just like putting it in 2D in a second. So what we want to do is that we want to have banking represent in some vector representation. And we want to have, like, for example, meet have in a different vector representation. And we want to have think in a different vector representation. And the distance between them in, like, visually, it looks like small. So the distance between those vector representation of meet and think, and those are like arbitrary examples, not like, put anything in them. So distance between them is going to be small. The distance between those vectors is going to be small, reflecting the nature of the distance between them that we perceive in the language. Okay. and so forth. Any questions? Yeah. That's what I'm going to talk about. Yeah, if there is a simple answer, there's no need to like, cover a module of this. All right, good, okay. So, by the way, so far I'm talking conceptually. I not talk about anything of technical value here. Everything is conceptual. And it's important before we go to the equations and whatnot and scare you, well, to talk about concept, like, why we are doing what we are doing, how eventually we want things to be, okay? So that at least when you get out of here, you can go and read the math later, but at least you understand conceptually what things are like, okay? And so there is a whole bunch of things that you have to add on top of this to make it work eventually. And by this, I mean what I'm going to explain in a second, like word-to-vec, the nicer one. Okay. So word-to-vec, this is your first friend for representation, how to get this compact vector from individual words. Okay. And by the way, something I'm going to explain today is going to make the assumption that you have already taken machine learning. Okay. Now we are becoming serious. I said, what is the prerequisite for this 6,000 level course? I said nothing. I lied. But it's too late to drop the course, right? So a little bit of machine learning, not a lot, a little bit. And I'm going to explain it as we go. So what is word-to-vec? Word-to-vec is this very nice tool, very nice technique that is used to build a compact, condensed vector representation for individual words that have all those fancy features we talk about. It has a similarity between words, like embeds words in vectors that have similarity, that captures the semantics, the meanings. It is compact. It's not so heavy. It's not so large that you have to carry it around for like large number of words. There's no space for them. And so it has those features. So the main idea is that we have a large corpus of text, a large amount, like large data set of words and neighboring words in their natural habitat. However, we just say them in their context. And every word is a fixed vocabulary. In the fixed vocabulary is represented by a vector, like the vector that we mentioned earlier. Okay, but short one. You go through each position T in the text, which has a center word C and a context outside word O, and then use the similarity of the word vectors for C and O to calculate the probability of O given C, or vice versa. And you keep adjusting the word vectors to maximize this probability. You understand anything? You should say no, right? Okay, so what do we mean by this? Here is the example. So let's say that we have a word into, and basically what I want to do is that I want to represent the word into by the different words around it. The word turning, the word problems, the word banking, the word crisis, and the word as. Not only that, but I want to get like a lot of utterances, a lot of phrases where into appears with different surrounding words, and I get representation for the word into from those vectors, stack them, and get this representation as maybe the average of the representations of into in a second. So let's talk about the word into alone. So how I want to define it, let's say that this is going to be the word that is a word. We don't care about what it is, into or whatnot, but let's call it W. Okay, T. This is WT. It's like a word W, in its index right now in the dictionary is T. So I want to define the word WT by its neighbor. So that is the probability for this word happening given the word into. The probability of WT minus 1 given WT. What is the probability of this given this? What is the probability of this given this? There's going to be WT minus 1. Okay, minus 1, minus 2, and then WT plus 1 given WT, and so forth. Make sense? Any questions? This is not math, by the way. Yes?
How do you prevent, like, essentially like data poisoning? Like, for example, if you have a typo in one of the words, how do you prevent your algorithm from being poisoned and getting wrong context clues?
Yeah. So this is good if everybody does that typo. Like, this is a problem. This is a good of a problem if everybody does the typo. So imagine that. How many people do this typo? Like, all. This is an edge case. I'm giving you a general case. The general case is for typos. oftentimes, they are not going to be very common. If they are common, you have to go there manually and fix them, right? But typos, especially in a large, diverse data set coming from different people for representation, typos are not the common thing, okay? And so here, I'm telling you about one type of instance of representation for into. But imagine into is appearing in million places and defined by million words. So when you take the average of them, the typo is not going to make a big difference. There's going to be a small, slight reweighting in the probability of into defined by the word before it.
So taking out the typo is one thing, but what about seems like you're locking everything down in this formula by sequence of the word, right? So
Yes.
You're figuring out what into means based on sequence.
Right.
What if people use different sequence or
that is fine. So that's not a problem, because eventually what I'm trying to do here is to get a lot of representations of into and get the average of them. So it's going to be encompassing to all the possible orderings that people use. Does it make sense?
It does, and then I assume that you figure out what into this. Therefore, it has
I don't right now. I don't care about like the structure. I care about like only the meaning of the single word, individual word. And the meaning here abstract to the computer. The computer does not really understand meanings. It's just a representation of a meaning. Make sense? Okay. Of course, and you can wait and you can do things. You are going ahead of the slides. So let me go over this, and then you can ask questions at the end. Any questions? Okay. So the idea is simple. Yeah. No, W is a word, and T, we're talking about like, you are, imagine that you are moving in a corpus and then trying to make representation for words. And so what is going to be the index? Why? WT? It's just like a symbol for a word. Call it X. Just WF. Could be X. Call it X. That's that we can just like, answer the questions and not explain the slides. It's going to be repeated.
So I'm assuming like not only for into, but given the solution is from problem as well, front and back and everything. So
Yeah.
Isn't that a lot of probabilities and computationally?
We'll solve the problem. Okay. So if you want to, like, for example, define into based on like, the start of the history and end of life, then this is too much calculation. So you have to live within a window. We'll talk about that in a second. Okay. So we have that for into. You have center word position. Call it into. It's going to be WT. And then you define WT based on a window size, like, a window size of 2, for example, 2 words before it, 2 words after it. And then you just like get a calculation for like the occurrence, how often into happens with turning, with problems, with banking, with crisis, and then get that as a vector representation. And then get another like into another context and so forth, and then get something from them. Then move to the banking. Similarly, you can represent banking based on words around it. And then move to crisis and so forth, and you can calculate the probabilities for them. Does it make sense? Okay. Are we good? Any questions? Buckle up. So now, what we want to do really is that we want to calculate this representation, L theta, let's call it, likelihood of a given bunch of words appearing together. L theta is a bunch of parameters. I'll show you like what theta would look like. That is going to be basically the probability of WT plus J given WT. Okay, WT we define it. WT plus J, we define it already. And basically what you want to do is that you calculate this combination, this kind of mathematical expression. You want to calculate, it's going to be a vector, right? You want to calculate it over theta. So basically what you are doing is that you are calculating this theta bunch of parameters from this equation. What is this equation? It says to you, it's going to be a product of bunch of probabilities of t from t equal 1 up to t capital. T capital is all the words in the vocabulary. And then t small is going to be an index. But for the inner product is going to be where minus m is less than or equal j less than or equal m for some window of m, and j not equal 0. Forget about that. That is not really important. What is important is that this basically, what is important is that basically you want to stick to the surrounding of the words, and you would not want to calculate a similarity between the word and itself. This is what we mean by j not equal 0. Okay, so what is this theta? Theta is basically all the weights that you want to optimize. Okay, and so how do you optimize them? You can just assume them arbitrarily to start. Okay, can we start arbitrarily? Yeah, we can start arbitrarily and adjust them based on some search in a way that they will match the occurrences that you have in the original probability. Moreover, they will be like satisfying some kind of norms, that the words that are similar to one another, they are close by each other, and the ones that are far from one another are just dissimilar to one another. The objective function here is going to be j theta, defined as j theta, and the objective function is going to be the average negative log likelihood. What does that mean? That it means that basically that the difference between the what you are calculating and some basic representation is as minimal as possible, and the average itself has to be minimized. So basically what we have here, this is the machine learning component, is that this expression that we have here, this is the probability, and this is the product. You want to basically get the log of this. Remind me, guys, who took probability. If you log something in the product, how do you calculate it out of the log? How do you get it out of the log? It becomes sum, right? And you put the log into the product. So basically here, what we did is that we calculated, we got from here, we applied, from here, we just applied the log for that, and we averaged it. It's going to be basically the average negative log likelihood, So average negative. Again, the calculation was over all t. So the average over all t is 1 over t negative. And this is basically the log of this, the log of L theta. So the log of L theta is going to be basically applying the log over the products. It's going to make some summations, and the log enters over those. Make sense? And so basically what we want to do is that we want to minimize this function, maximizing the predictive accuracy. That a given word predicts its, the given neighbors predict the word itself. Make sense? Yes.
What is the, I know the straight bar WT, but what is the semicolon and theta in?
Conditioned on the, like, basically calculated for theta, for all theta. Theta is all the parameters, all the variables they're trying to optimize.
Theta contains all the weights of all the words, or just that particular?
All the words, yes. I'll show you the expression of that in the next slide. Okay, so you have like a vector for each word. For all the words, you want to calculate this probability of WT plus J WT for this window. Okay. Oh, scary. Any questions?
You said that you can start arbitrary and you can optimize some probability.
You don't want to do that. We'll talk about that in a second. Yeah, I'm still like, one possibility is start arbitrary. You don't have anything. So that's why I said like you can compare to a ground truth. Like, for example, with this one, with like, how do you find a loss function, for instance, for this, right? So you have an annotation of, say, for example, on the corpus, these words appear together. If based on the output, it do not appear together, then you have to, like, basically correct for that. So you have, come again? You can have the ground, you can have the ground truth, because this learning is going to be supervised. I'll give you the example at the end, and then you ask me the question if the example is not clear. So why do you want to have a ground truth? You can have like what we call, like, for example, a weighting function that says that those two words are actually similar and not similar, and from that you can calculate the loss. Make sense? Okay. All right. So again, the objective function, we want to maximize the objective function, which is going to be basically this one is what we have just explained earlier, is going to be the negative, the average of the negative log. And the question is basically how to calculate this BWT plus j given wt theta. We will use 2 vectors per word, 2 vectors for each word. VW, when W is a center word, this is when we want to basically capture the words that define it. And UW, when W is the context word, that is for the word surrounding. And then for a center word, C, and a context word O, basically we calculate the probability as B of O given C as the, this formula. Can anybody tell me what is this formula? Softmax function. What does the softmax function does?
Yeah.
It maps values from 0 to 1. Basically makes anything into probability. Okay? So again, we have 2 vectors. There's going to be VW when W is a center word. It's going to be representing for the word when it's a center. And UW when the word is a context word. And then calculate the probability for the outer given the center as just the multiplication of those 2 vectors that we have defined earlier in the expo over the sum of the multiplication for all the words in the vocabulary. Does it make sense? Softmax makes sense? Okay. So we have, yeah, in the vocabulary here, the W and V. That's how you calculate as a probability. Okay. Any questions? So basically, you are trying to basically. We said earlier that the word in the outer define the word in the center. The words in the outer, the surrounding words, define the word in the center. And this is what we want to calculate as a probability. So we have 2 vectors. 1 vector for the word when it is center, and 1 vector for the words when it is outer, right? And so those 2 vectors, this is, by the way, is inner product. This is a vector representation. So let's say like a vector of 100 values. To multiply them, they are vectors. To multiply them, one of them has to be a row and one of them has to be column. So you can imagine this is the column and this is a column, right? So you have to transpose it. This is T, transpose. Okay, algebra. Understand what I mean? Transpose, right? Transpose means that you have 2 vectors, they are columns. One of them, you rotate it, transpose it, so that you can multiply them together to get a value, single value. And this is going to be a value of the vector when it is, again, you see a U when W is a context word. So this is for U, and this is V for the word when it says center. This is for the outer, this is for the center. So you multiply them, and you get exponentiation of them. Exponentiation of the value is going to, what does the exponentiation do? What does the exponentiation do? What does it do? Yeah. Positive value. That's called, we want to calculate the probability. Probability cannot be negative value. Okay? You want to calculate the probability. The only reason we are using this exponentiation is so that we can do 2 things. Like the only reason we are using this is for 2 things. One is convert into negative positive value. Second is basically to boost some values higher, reduce some values lower. We'll talk about that later. And then over, eventually you have some values to calculate it, to make them as a probability. What do? You divide by all the values, all the possible values, right? So this is like, for one presence for a word, a given word. Then you divide the same thing here. It's the same thing, but you divide it over the sum of all the words in the vocabulary. Make sense? And you get the probability. Okay, yes.
Isn't one of the words in the vocabulary the center word itself?
Yeah, that's fine. Yeah. Okay. So that is that. Again, so you start with, like, say, the word into. You calculate the probability of turning given into, of problem given into, with banking given into, and with crisis given into, and that's going to be the representation for the word into. Eventually, what you will have is going to be this equation. We had it earlier. So it's going to be the probability of O given C. This is a predictive function. And so this is going to be calculated as XUO transpose VC and over summation of W in V for X, U, W, T, V, C. And so this is like, what we have, just what I explained earlier. The exponential should make anything positive, and the dot products that we have here between the vectors compare similarity of O and C, and calculate as follows. Like it's going to be, dot product is going to be basically pairwise a multiplication, and then you sum them. You sum the values of the multiplication, and then the lower part is to normalize so that you can calculate a probability based on the entire vocabulary. So this is an example of the softmax function that you guys just recognized that maps a value from Rn to Rn. And Rn means real value of size of dimension n. And so the softmax function maps any arbitrary input, say for example, xi. In this case, it can be anything to a probability distribution pi. The max is said because it amplifies the largest value xi, and soft because it still assigns some probability for small values. And it's frequently used in deep learning. So that's why I said like machine learning in this space. Any questions about this? Okay. Let's just skip this. So training a model to be able to achieve this kind of work is basically by adjusting the parameters to minimize the loss, maximize the accuracy of representation. And so the loss is, for example, can be the error. So let's say that for the simplest example, let's say that we have words and the words are indicative. We'll not talk about like representation, indicative of positive, negative, something positive, something negative. Okay, make sense? So you can assign the values like 1 and 0. 1 is positive, 0 is negative. What is the error here? The error here is that your model itself is saying to you about the positive to be negative and the negative to be positive. You can calculate the difference between them. So if it like the model says to you 0 when it's supposed to be 1, you have an error of 1. You accumulate the errors and then add them together, and then you have the total error. We call it loss. Loss. How the model is different from the ground truth. And then what you want to do is that you want to minimize this error by adjusting the weights of the model. Similarly, in this representation, you start with some representation that says something about the definition of the word given its surrounding, right? Whether it is center word or not, based on the original assignments that we have. And then you adjust the weights so that the overall error is minimized. Make sense? Yeah. For a simple complex function over 2 parameters, the contour lines show the level of objective function, and you can decide whether, like, how you will move those weights accordingly. So to answer your question, what is in this theta? In this theta is going to be the vector representation of all the possible words. And we said that for each word, what do we have? We have 2 vectors, right? We have something that defines center and something that defines outer, right? Each of those vector representations is going to be of size D, right? We don't want to use V. V is too much. We want to use D, short representation. And so basically theta is going to be a bunch of parameters. The size of this theta is going to be real values of size 2D by V. V is the number of vocabulary in the dictionary, the number of words in the vocabulary, and then D is going to be the size of each vector, and 2 for each of those. So every word has 2 vectors, and we optimize these parameters by walking down the gradient. So again, what you do is that you calculate for each of those words 2 vectors, one when it is center and one when it's not when it was not center. And generally, in each window, we will compute an update for all parameters that are being used in the window. Okay, any questions? Intense, right? Any regrets? Yes. Yes. This slide. So it's going to be your representation of the dictionary for each word. So each word has a couple two vectors, each of which is of size D. One of them when the word is defining other words, and one of it when it is not defining other words. Positive, negative. Center, not center. Okay? And so this basically theta is the one that you want to calculate.
That's 2D.
Yes. 2D, 2 vectors for each. So we optimize these parameters by walking down the gradient, meaning that, like, you know, we start with something that is arbitrary. Arbitrary is a bad idea. We start with some calculation of probability we'll talk about in a second, right? Okay, so let's move on. So more details. Why 2 vectors? Why do we use 2 vectors? From optimization standpoint, it's easier to work with 2 vectors than with 1 vector. Okay. The 2 model variants, you have a skip gram, which predicts the outside, and continuous bag of words, or CBO, which predicts the center word from bag of context words. So far, when I was talking about it, so far, I have defined it with what? With defining the word by its neighbors, right? So we can use skipgram also, predict the context, the outside word, based on the center word. Yeah.
Seems like you could create a value that was exactly similar to something else based on positions.
Based on the position, we do not care about the. No, it does. It does. But that is if only if the word is only defined by the position. And here, I don't think that the position itself is important. It's the fact that it is surrounding the word is important. Because so far, I have not assigned any probability different to the word based on its distance from the center word. You can do that, by the way. And most good models would do that. But so far, I have not really talked about the distance. Yeah, please.
This process moves down the center.
Yeah.
So what was one P?
Yeah.
And P -1 or +1, probably +1, now becomes P. Like as it moves down the process, there's this moving. There has to be some sort of moving. And does it compare back to what it just figured out? Does it make any sense?
And I'm not following the question.
So in the word into, we're following it, then eventually becomes the word that goes back into.
Right, right. So into defines the word after it.
That's right.
Yeah. So what is the question?
Does it take the value or the vector from the previous compilation?
No, 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 no. So for the word into, we calculate a bunch of vectors. For the word after into, we calculate a bunch of other vectors. Separate one. And you know, in the case of this example, you might think that like, oh, the word before into is related to the word after into in the representation. But only we know because we see it. It might be that this is the only utterance in the language where this happens to be the case. Make sense?
Yeah.
Okay. Yeah.
You said you could purely because you took the words one minute to find what is the pattern, right?
Yeah.
Like, does it have like immediate next word for after?
Immediate. You know, you can skip, you can have like a large window, small window, you can skip words, you can wait words, you can remove words that you think that they are not, like, so far I'm talking about the abstract, simple kind of technique. You can remove words, you can say like, oh, this word is just like, you know, it's a typo. It happens to be like defining this word in a negative context. I don't want with this negative context to define this word. So I can remove it. I can, yeah, you can do a lot.
The second vector is the same vector representation. That's coming from the same probability function from the softmax, or is it some?
It is, yeah, it is, yeah.
One vector is connected to the second, another vector is one.
Yes. Okay, so additional efficiency can use negative sampling. We'll talk about negative sampling in the next lecture. It's going to be a whole thing, but you know, for now, let's go over the example. We are running behind time, and so we'll have a cost function. Let's call this cost function J theta. Remind me, what is the cost function that we talk about? It was the loss, right? The loss. And so the gradient descent is an algorithm to basically minimize J theta, to minimize this error. We'll have an example of that algorithm in next lecture, so we don't have to worry about it. But for now, what we care about is its name. What is the name? The gradient descent. How many of you, by show of hand, how many of you studied gradient descent in other lectures, in other classes? Did you have like an example, like a numerical example for it? Like how it works so that you feel it? You did? Did you have it? Did you guys have it? So if I ask you, like, you know, you had it, right? In which class? Oh, machine learning. Okay. So Okay, so statistically it's easy, but like, to go over it by example, we'll go over it like next lecture. So for now, let's say that you have a bunch of values theta. These are the parameters, and you want to basically change those parameters, those values, so that the loss itself, j theta, is minimized, that the accuracy itself is maximized. So how do you change those values up and down? Okay, it's going to be based on what? Based on some derivative. Okay, so like if you want to minimize the loss, right? You must minimize the error. You have to reach a value where that error is minimal. Then there is a slope, there is a sign for the derivative that dictates where you go. Okay, that's what we do. So basically, the idea: current value of theta, calculate a gradient of j theta, then take a small step in the direction of the negative gradient. That is, you are just heading towards the zero of the loss. Okay, this is what you do. And when you have like the minimal value, there's going to be basically the maximal accuracy. Okay, mathematics, right? It's not very difficult. So basically what you want to do is that you want to update those parameters, call them theta nu. Theta nu is going to be theta old minus something that you remove from this weight, right? Okay, what is that you remove from this weight? It's going to be the difference in j theta multiplied by something what we call a step size or learning rate. You learn about that a lot when you are doing with those models. It's called alpha. Okay, so alpha is a step size. So basically, you are modifying this theta little by little, from the old to a new one, in a way that it would eventually result in the maximal accuracy, the reduced error. And this is the equation that you follow. You update the equation for a single parameter using this. We're not going to talk about this very much, but next time we'll talk about it with actual example numbers, concrete numbers, small numbers, so that we understand it. The stochastic gradient descent, what is the problem with this one? What is the problem with this one? Remind me. Huh? Okay. Many data points. So stochastic is that you sample some data points, and then you update the values based on that. Okay. So let's talk about example of word-to-vec, which is the end of this lecture. Okay. So the objective is basically to convert a corpus into a format for word-to-vec. So you take this like data set, and so these corpuses are going to start with a large collection of text, like for example, the cat sat on the mat. And the vocabulary creation will be identifying the unique words, each unique word in the corpus, and it's going to be represented. Okay, so eventually for this example, we had the cat sat on mat. Okay, because that mentioned it twice, so you just like have it once in the unique vocabulary. And then we have the context window. We define a context window size, let's say n words before and after the target word. Why don't we use like arbitrarily large number of words to define a given word? Quick. Can you think of it? Huh? Why do you do that? Why do you have to do that? So one of it is computational, right? One of it is linguistic, right? I like the word scope it out. Why? Because some words like far away do not really necessarily define anything related to the word. So it has to be the words that are really near it, like 3, 4, 5, right? 7 maybe. And then if you want to go even like larger with larger attention, you have to weight those words that are closer higher than the words that are far apart. Okay, so that's what we do. So basically, we define a context window, n words before and after. In this case, let's say that we have the n to be 2, right? And so for the word sat, the context is going to be the cat on the. Okay. Then you choose a word-to-vec model. A word-to-vec has 2 architectures: skipagram or CBOW, right? The continuous pack of words. For the skipagram, predict context word given the target word. In this example, we have the word sat. We predict the cat and on. And if we are using the CBOW, then predict the target word given the context. And in this case, for the cat on the, you predict sat. Make sense? And every word is going to have the chance of being a center word, so you can basically predict it. Make sense? So eventually, you'll have probability distribution that conveys the same thing. right? But the way that you reach that distribution is going to be different. All right. So you create then a training set. There's like, who said the error? Training set, right? For each target word, generate input-output pairs. What are they going to be? For the skipogram example, we have the input sats and the output is going to be cat on. And for the CBOW, we have the input is going to be the cat on the, and the output is going to be sat. And you can add some negative samples if you want. That is where the error comes from. Negative samples. These pairs will be used to train the word-to-vector model. Okay, so those are the words that happen together. You initialize a word vector embedding. What can you do with initialization? There are two approaches for this. Okay, you can use, what can you use? Randomly or uniform, right? Or like the nicest one of them is what? Some pre-trained model. You use some like, weights that you get from the other world and have them. So you create two matrices. You have the input embedding matrix and the output embedding matrix. The input is like what you can start with, and the output, what this black box is going to produce for you, and use that as your eventual representation, the good one, the one that captures those relationships between those words. Okay, so the size of each matrix is going to be the vocabulary size multiplied by the embedding dimension, and the embedding dimension is oftentimes small. So if vocabulary size is 5, the embedding dimension is 3, the dimension of this is going to be 5 by 3. You train neural network. Shallow neural network is used for input layer, hidden layers, and output layer. We'll talk about those in deep details later, but I'd assume that you really know something about those a little bit, maybe. So the one-hot encoding can be used as an input representation. The hidden layers are going to produce the word embedding or dense vector representation. And those, after you calculate, you'll get them as your output. And then the output layer is going to predict the probability of the context word given the surrounding word with the softmax function. You have forward pass, you multiply the one-hot encoders with the input weights, adjust them, and then eventually the adjusted ones are going to be your eventual representations. Use the regular thing that you use for neural network with the loss function and whatnot to make sure that your initial data set is intact. And so eventually you start with a word representation of 101, 011, 010, 011, and you will reach weight representation of, like, say, for example, 0.25, 0.75 for cat. For dog, you'll have 0.60, 0.80, and then for mat, you'll have 0.1, 0.9. Can somebody spot an error in this slide? What is 3 vectors? Yes.
Dog is
Which one?
the dog.
Yeah, that's right. It was intentional, by the way. Okay. Yeah. Okay. You guys get the point, right? Yeah. What was that? Yeah. 0.6 and 0.8 is not a probability. Yeah. Okay. Any questions? Somebody had a question? Raise their hands. Yes.
That's like equal distance from the, like cat. You have these two.
Oh, okay.
So maybe like
I skipped a little bit. So basically you have an input representation and you have an output representation, right? You know that those are actually related to one another, the words, right? And you have the input representation. The input representation is going to be like one-hot encoding of the words. And then in the middle, there's going to be the matrix W that is going to be mapping the input to the mappings. Make sense?
W could be any could be a sign.
W is going to be the mapping function that says that those words that I have inputted are going to be defined, like similar or not similar, or defining or not defining, right? Because I have training pairs here. Here's my data set, right? So this training data set is going to be basically for each target word, you generate input and output pairs. Okay, and so basically this part here, the dense vector, is going to be W. And like in W, there's a row for each input word. That's what it is. Make sense? Are we good? I know what you're talking about. This cannot be 2. It has to be 3, right? Because you have 3 words. I already said that, but this is an example. Okay? Makes it 3. It has to be 3. It has to be a full matrix, W. I'm too lazy. I know how to type them. It's to highlight the idea, right? This is like, no, it cannot be like, basically two or three words or whatnot. To highlight the idea that this is going to be a distribution list. Okay. All right, takeaway. So word2vec represents words as dense vectors. We've seen that. Unlike sparse encoding, word2vec uses shallow neural networks, skipgrams or CBOW for initial representation of bearings to learn embeddings that position similar words close to one another. And we have that already in the training set. And then these learned representations improve NLP tasks, and we will see that down the road. Any questions? Yes.
I was thinking about how.
Yeah.
Like we think about the same algorithm and cause some kind of collision, and cause some kind of race condition where it's just us and lost.
Well, there are so many ways to attack this. For example, where do those like representations come from? They come from a large amount of data. And so you can imagine that there are certain words that are different, but happen to be based on this data, happen to be close to one another in the space, in the representation, in the representation, right? And so what you can do as an adversary is to add a little bit of salt, inject some poison, some noise, perturbation, some noise in the input data so that they can be even more similar, to be confused with one another. So that, like, for example, a through shot that you use, like a difference that you can use for distinguishing between words no longer works. You can do that. It's like word poisoning. You can use it to make the word mean something different than what's supposed to, or maybe like, make some words collide, like, become more similar than they should be, right? It happens at the, like, I don't think that we talk about this in the semester. We talk about that when we talk about like the security class. So you can poison the data set, you can poison the model, you can change the parameters in the model that this kind of behavior happens. You can change the even the decoding. So we're not talking about decoding here, but there could be a decoding phase where the output of the model itself has to be processed afterwards to get something, and then the decoding process can be itself poisoned. So it can be happening at the training phase, can be at the training data itself, the training process itself, the model itself, or the output. And that was like part of the security class. Like, I don't think the security class, we can talk about that later. Anything else? Any questions? We have attendance, right? All right, be coming. All right, guys, online. See ya. Tonight, ask any questions about the proposal. We have an office hour today.